and momentarily we'll be starting our next presentation, so please take your seats. And welcome to introduce Sebastian Garcia, who's a university student and part of the next generation of security personnel, professionals, unlike next-gen firewall and next-gen everything else.
Well, thank you very much. That's too much, maybe. Okay, so welcome, everyone. How are you? Thank you very much for being here. I'm Sebastian Garcia. I'm a researcher in Czech Technical University here in Prague. So it's very nice to be here, and I don't have to move a lot. It's very, very nice. And I'm going to talk about how we are modeling the network behavior of malware using behavioral patterns. And this is a research that started a long time ago, and we are doing it in the university. And especially, we are dealing with the network here, right? So when you work with malware stuff, botnet stuff, and you are trying to detect behavior, it's completely different if you're doing it in the network, if you're doing it inside the host or inside the binary, right? So we are dealing with network security here. Who in the audience is working with network detection at different levels and not in binaries and all this stuff? There, someone there, here. OK, thank you very much. So please feel free to join and say, hey, that's wrong, or something like that. So actually, when we are working with network solutions, there is a lot of research. But when you have an issue, when you have a problem, and you go to the network and you want to fix it, this is what we have now. This is the best we have now, right? So we have some indicators of compromise there. And this is domains, URLs, IP addresses, and you got this, and you download the whitelist, blacklist, some feeds, and you say, yeah, I should download this, put it in the firewall. And if not, you're running something that has some fingerprints in there. And say, OK, payloads, right? I can run Snort or Bro or something. Bro, actually, it's not with fingerprints. It's with a very nice language for detection. But this is what you have. And if you're getting really complex, you're going to say, hey, I have anomaly detection here, right? So who is running some anomaly detection technique at some point in the network? You are. This is very nice. And there, some anomaly detection. So the people is going here. So machine learning, artificial intelligence. And one of the most famous techniques is anomaly detection. And I have to say that this is the best we have. But unfortunately, this is not enough. And if you're working in this, you know that at some point, this is not working, right? So we have some issues in here. And the issues are that, for example, which is the lifetime of these indicators of compromise? How long should you use a domain to be blocked? How long should you block an IP address? How long some URL pattern is going to work or not? And these lifetimes is very difficult, right? I don't want to go deep here, but there are some analyses and say, hey, yeah, I'm putting this in the list for 1 month, 15 days, 1 day. You never know, forever. And then you have the verification. Like, OK, yeah, we have this domain in here. We have a host name. And who is verifying that this is malicious? Well, fortunately, people is verifying it, right? Unfortunately, people is verifying it. So if you go to, for example, VirusTotal, and you search for www.google.com, you will find that you have like 7,000 of people say, no, this is malicious, and you have like 18,000 say, no, this is good. No, this is malicious. No, this is good. Because verification is very difficult. You know Google is really an address that everyone is accessing, so malware is accessing, we are accessing. But if you are trying to automate this, verification is crucial. So most of this stuff is very difficult to verify, and that's why you have these errors in there, right? Another issue is the huge amount. A malware can generate dozens of IP addresses, dozens of URLs, dozens of domains. And at some point, you cannot block them all. You cannot put in every device like several thousand rules for block everything. So you go to patterns, you go to fingerprints, you go to anomaly detection, and this becomes an issue more and more. Also, a lot of these solutions are static. So they are not evolving in time, so we should update it every time, again and again, and they are stop working after some times. And in the case of anomaly detection, I'm not sure your experience, but in my experience, it's very hard to make it work, very hard. It's working, the context should be very small, and you should do a lot of work in there, and at some point you have something. But very important is that you say that you are detecting anomalies and not something malicious, because an anomaly is not by default something malicious. An anomaly is an anomaly. So you should have people there checking if those anomalies are actually malware or threats or not. So this is not easy job. And actually, we think that we can do this better, we should do this better, and that's why we are going to talk how we can work with behavioral models in the network using machine learning to detect botnets and malware and these attacks. So we think that machine learning is actually something that is very helpful, and it's going to be more helpful if we can do it properly, but we should keep working on this, right? So what I'm going to present you is the Stratosphere IPS project. This is the project, we are having in the university. It's our main project in security and malware detection, and we have 4 main ideas in here. So the first one is free software. It's free software. And why is that? It's because we need this software to be verified by others. We need this machine learning and these behavioral patterns to be checked, to be implemented, to be tested, to have errors, to solve the errors. We need the people to see what's going on. And also, other of the main ideas of the project is to focus on NGOs and civil society organizations. So some years ago, the Citizen Lab group had a report on targeted threats, and they say something very, very nice. They say that usually NGOs and civil society organizations are attacked very, very hard. They are attacked with very, very important malware from very important actors, but they don't have the money. They cannot afford buying very nice solutions, like I'm sure most of you can sell in antivirus companies. They cannot afford it, right? So they have there a lot of organizations that they have very important problems, and they cannot solve them. If you know Claudio Guarnieri, he's going to lead a talk tomorrow, I think, about helping the helpless. And I highly recommend you go there, because he's going to talk a lot about this. And I thank Claudio, because this is part of what we are trying to do here. We try to focus in helping NGOs and CSOs. And for that, it means that we should take privacy into account very seriously. And that's why the free software is also here, because we need to be very trustful, OK? And the other part is the verification. So since we're a university and we are doing this research, we want it to be verified. And this is hard. You know it, right? If I'm asking you, OK, you have some products, some really nice products, and do you know how good it is? And this is a hard question. You don't know. Yeah, it's good, but how good? How you compare it? How is this changing in time? So verification is very important for us, and we are going to talk more about later. But in the Stratosphere IPS project, these are the 4 main ideas that are driving us to create it. So technically speaking, which are the pillars in here? And I want to be very brief. I'm not going to go too much into details. We can talk it later. But we start saying less is more. This is one of our main goals when we are dealing with machine learning. Less is more. And then we are going to talk about how we came to the idea of disassociation, disassociate the models in the network. And finally, the third pillar is the verification. So this means that when we analyze the behavior of the connections, we are not focusing on what your host is doing. We don't care about what's happening on your network. We are focusing in one and only one connection at a time. And this is giving us a small amount of data that it's good data, but it's small enough that we can deal with this with machine learning algorithms. And then we can go back. So we are going to work first with less amount of information. We don't want to run an anomaly detection in the network per se. And another main idea here is the disassociation. This means that we build the behavior of the network, the representation, and we are separating it from how we detect this behavior. So first, we are going to work and do some research on how can we represent this behavior. I don't care about detection yet, so I'm not thinking about any fancy algorithm yet. And now that I can represent the behavior I'm looking for, I will stop and will start trying different detection methods on this. Usually, when the people is researching, I cannot use my hands, but they are doing this all together, right? They are putting all the detection methods and all the representations and the packets and the floats all together. They run an algorithm, and it's maybe working. But this is very hard to scale. So we are going to disassociate, and I'm going to tell you more. And finally, this means that for verification, we need real and label normal and malware data, OK? Without the real and good data sets, if you were in the keynote, the speaker was talking about how they were creating a very large and important data set of cyberware or malware and binaries. OK, that's what we are looking for. Not binaries. We are doing it in the network. But we want to have a very nice verification with real data. So going to less is more. What less is more? This means like when you are connecting to some service in the network, like Gmail, or you are listening to music, or you are chatting, when you are doing that, your behavior is usually the same, right? You are human beings, so we are behavioral by nature. And when you are using it, when you are trying to access a website, you have patterns in there. You are changing a lot, but you are not random. So you are doing it in a very, very similar way. And the malware, in some senses, is not different to that. So what we are doing is that we are grouping all the flows. We first get the packets, then get the flows, and we are grouping all the flows that are going to some specific service. Like, for example, port 80 in the IP address of Google, or some port for SSH, or email, or whatever you are connecting. So we are only taking these flows all together and say, OK, these are your flows when you connect to Google. And actually, you don't care if you are connecting in today, and then in 5 days, or in 1 hour, or whenever you are connecting. When you are connecting again, I will get your flow, and we'll put them all together, right? And then we have that this connection that is composed of several flows now shows a behavior. This connection, if we wait in time, it's starting to show in a behavior. And that means that when you are, for example, browsing Google or using Gmail, maybe you don't notice, but you are going from one state of your behavior to another, like sending email, not sending email, chatting, not chatting, sending a file, not sending a file, doing nothing and be the little, play music, download the video, don't download the video. So we can recognize these states, and we want to be able to work with these states in the connections. So each flow inside the connection, it's getting its own state, OK? And we model these states based on these 4 features. And I ask sometimes, like, why these 4 features? That you can use like several dozens of features. Yeah, we can use hundreds of features. But after a lot of research and working with very complex model, we find out that a very simple model with these 4 features is the best we can do, because we can understand it. So we are taking the size of the flow. Look at the features. They are very simple, right? Size, duration, the periodicity. This is not easy. I'm not going to talk here about the details, but periodicity is quite a computation in there. And then we have the time between the consecutive flows, OK? So 4 features. What are we doing with these 4 features? OK, so every time I got a flow in the network, I'm saying, hey, how is your size? It is small, or is it medium, or it's large? You can see that there are, OK, under this there are some numbers, but I want to show you like the big picture here. The flow is small, or is large, or the duration is short, or is medium, and the periodicity is strong, or actually is strongly non-periodic. And now we can assign to one of these states a letter and say, hey, so if this flow is not periodic and is small and the duration, I will give you the letter J or H. And we start assigning letters to each flow in the connection. And finally, you can see that we are using some symbols in here to put a threshold between flows. Because if you have a periodicity of 5 minutes, it's not the same as a periodicity of 1 day or 1 week, right? So we want to detect that. And we are saying, hey, between flows, less than 5 seconds. Between flows, oh, no. We have a timeout of 1 hour, so you should put a 0 here. So let me show you what we are doing with these letters in here. So I will show you first, using part of our Stratosphere project, I will show you that we have a lot of data sets in here that we are analyzing all the time, and this is a normal connection. So here you can see a lot of connections in there. These are the type of connections that are going from one IP to another IP, and then are going to some port, right? I just stop it. So one line here is one connection, this IP to this IP, this port and TCP. Can you see it there from the back? Yeah? OK. So and each flow in this connection got a letter, and there you can see the letter, right? So look at here. Like we have a web page, and we have some a flow that is getting a 0 point. So if you see a point means very fast. So the flows are here coming very fast. But these are not periodic, because if you look at the periodicity in the chart, the periodicity is only from A to I, right? A to I. More than I, it's not periodic anymore. So I can look at it and say, hey, I'm a human being. Hey, I can say, this is not periodic. But here we have some periodicity, very fast periodicity. And then he loses the periodicity. Then we have something like 5 minutes. And then again, even if you look at it, you can see a pattern. Look at this. It's like 0, 0, I, 0, plus. 0, 0, 0, I, 0, plus. 0, 0, 0, 0, 0, 0, plus. 0, 0, 0, I. So you can see that there is some behavior in here. And actually, this is a normal capture, remember. And this is a web page that is showing some information that it's being reloaded every 5 minutes. So there is some JavaScript in here, and it's reloading. But even if it's reloading, it's not periodic completely, right? And then here, for example, you have a normal web page, like nothing fancy. So just access a web page. So you can see, like, I don't know, 10 flows, no periodicity in here, very fast, because it's downloading the images, it's downloading some JavaScript, that's it. And then here you have, for example, some SSL connections, right? Also no periodic, very short. As you can see, I don't care about the payload, so I don't care if it's encrypted, it's not encrypted, it's SSL, it's TLS or something. If you are behaving, you are doing it all over and over again, right? So let me show you now some, for example, I will show you this MuRef botnet. So this MuRef botnet, is doing more stuff. Actually, I didn't tell you, but I'm speeding up the flows, right? This actually is like a 4 or 5 day capture. So I'm speeding up the flows so you can see what's going on. So you can see some connections in here. Red is UDP, I don't care, DNS, some IPv6, ARP. And then we have here some TCP connections to port 80. And if you look at the connections, you will say, hey, this is very periodic, I. And actually, the timing is less than 5 minutes. So this is a very periodic behavior. And if you look at the traffic we did, it's a command and control. So here, we can capture the behavior of a command and control that it's doing something in MuRef botnet. Also, you can see that there are other connections, but they are not periodic. That means that MuRef is using several types of connections. Some are for command and control, but some are not. Some are, for example, to download stuff, to get some images, or just to send information. So not everything coming from this botnet is having the same behavior. So we are focusing on this, and we are saying, hey, I can build a model to detect that. And this is completely different from the normal traffic. I only show you one, right? But we have several, and the normal behavior is completely different. So if you, as a human being, looking at this, can make the distinction, so an algorithm, it has a good opportunity to do this, right? To do that. So I'm going to show you another one. For example, the Geodo botnet. There. So it's another connection. And you can see here that there are also periodicity, but it's half an hour or something. And then look at this. There is a loss of periodicity, some zeros. The button is not periodic anymore. And now we have another connections that are completely not periodic, but you can see that there is a pattern in here, right? And look at this, a new connection, new command and control, because the old one, it's not responding anymore. So we have a new sending of information in there. And also, look at this. Each zero is 10 minutes. Each zero is an hour. So we have here like 7 or 8 hours between flows, right? So this is part of the behaviors that we are looking for when we are analyzing the traffic. So when we have the behavior, what we are doing, say, OK, so why we like behaviors? And we are saying that malware generates the same behavior over and over again. This is something that we just saw. Also, changing the behavioral patterns for the malware is very costly, because if you stop being periodic, you cannot communicate with all your bots at the same time, and you cannot send commands at the same time. So at some point, you are losing some of your power if you are not so periodic anymore. You cannot update so easy. It's not impossible to change it, but it's costly, very costly, right? And then the behaviors do not expire so easily, because you need this behavior. It's part of what you're doing as a botnet. And then the infections go unnoticed for several hours, usually, when somebody is infected. So we have time for this. If you need 5 minutes, hey, 5 minutes, you can get them. 1 hour, it's OK, right? You don't get someone like trying to detect a malware in the network in the first minute. Usually, if the administrator have to go there and clean the computer, it can take several hours. And then we collect normal and infected from malware behavior. So this is what we are using behaviors. So after we got this, we are going to apply some detection models. So we have several. Now we are running 2, and 2 more in development. And the first one is we are going to interpret this as a Markov change of the transitions. So our first detection model, separated from the model of the letters, that is the network model, our detection model is looking at the letters and saying, hey, I want to see how you are going from one state to the other. And I'm going to build from this a matrix of how you are going from A to comma, comma to A. I will count this. I will have the probabilities in here. And I will build a Markov change. I will say, hey, this is the model of behavior of how you are changing from one state to the other. And once you have that, what we are doing is that we are training these Markov models in known behaviors. So we are verifying by hand, this is button, this is malware, this is normal, this is more normal. We have traffic from the university, from companies, and we are spending time on this. But once we have the behavior, we can compare to unknown behavior and detect the stuff that we don't know. We can say, hey, this, I have no idea what it is. But if I compare to the models I have, I can get the model that is having the same behavior. And this is good because the models can generalize. I don't have to detect exactly the same pattern. I just need to detect a similar behavior. So I can say, OK, it's not exactly the same what you're doing because the timing is changing, the periodicity is changing, but you are behaving in such a way that this is not normal and matches a malicious behavior, right? So we compute the winner model. And at the end, we want to know, hey, is this working or not? Like, how are your results going? Like, do you have some results? Well, actually, we have results. But if you ever try to verify how some software is working in detection, you know that this is a very difficult question. It's like asking an antivirus how good it is. Good how? Good where? Good when? Right? So it depends a lot how you are verifying your software, the results that you have. Actually, it depends on the data set. I can show you data sets that the detection is perfect, but that's not real, right? So we are plugging it in the network, and we are detecting more stuff, and then we have errors, and then we are improving. So it's very difficult to say how good it is, any software. For ourselves, our software is working very good, right? And that's why we want to verify and show the results publicly. That's why everything is free software, and even the data set, you can download all the malware from the web page. So we have this large public label and real data set with normal, malicious, and hybrid behaviors. And what does hybrid means? And this is very interesting. Because if I give you a malware traffic, and you can detect it, and then I give you a normal traffic, and you are not detecting it, the detection rate is perfect. Your false positive rate is amazing. But what we are doing is that we have normal computers with real people, and then we're infecting them with something that we know. Then we continue doing the normal traffic for several days, I don't know, Facebook, Gmail, whatever you're doing, and then we are cleaning the computer, and we continue having the normal traffic for some days. So we have 1 week, 2 only normal, 2 days that are mixed, and 2 days that are clean again. So I want the software to say, this IP address is clean now. Hey, now it's something infected in here, and now it's clean again. So we are trying to make this evolution, right? We are not trying to say it's infected and that's it. And finally, we are comparing different approaches, which is actually crucial for predicting the performance. So we are going to stop in here. I will say that the network behavioral patterns work really well for us, and I think that is something that you should consider researching if you are not doing it yet, because it's different approach of machine learning. It's taking some behavior that you know, create the machine learning from that, and then detect it, right? It's different from anomaly detection. So thank you very much. That's my contact information. I don't know if we have some questions or something.
We have some time for some questions. Are there any questions? If not, I've got one.
It was quick, sorry, but it was, yeah, half an hour.
So you're taking a look at known bad behaviors like by botnets, and you're able to identify patterns, but in order to avoid false positives, you're going to have to compare that to a huge variety of software. Have you found similarities between botnet patterns and enterprise security control, such as pushing patches or
well, actually,
stations?
yeah, I understand. So some behavioral patterns have similarities. Like, for example, antiviruses, they're updating, and from time to time, that updating mechanism is looking like very periodic, very small, right? And at first, this looks the same, but there are a lot of differences, not only in the flows, but how you are doing it, like how is your periodicity working, and more importantly, which other connections are coming from your computer. So I didn't talk about that here, but when we are comparing and saying, okay, you have the traffic in here, is this malicious or not, we are taking all these connections, and we are seeing, like I show you in the traffic, like, okay, here you're doing something, but then you are doing something very, very strange in DNS, for example, and you are matching 2 or 3 or 4 or 5 different models. So then is when you say, okay, this is malicious to this degree, confidence, trust models, right? So you have some verification is there. It's not that you say, okay, you are periodic and that's it, because there is a lot of normal software that it's periodic, right? And actually, it's funny, but botnets usually are not so periodic. They are having periodicity only when they are idle, when they are doing nothing, when the command and control is just waiting. But when they receive an order, they are acting, they are doing something, they are attacking, and they don't need to be periodic anymore, right?
I think we probably have time for one more question.
Oh, at the end. Oh, yeah.
Randy?
They told me to point the people, so. Oh, thank you for your question, Nana.
Thank you. Have you considered like protocols where like UDP getting tunneled over TCP and all that? How are you considering those cases?
Sorry, UDP protocol?
When you have tunneling protocols, like
tunneling protocols, yes. Well, we have a lot of different cases that are very difficult to match. For example, tunneling is one, and also you have, for example, under NAT, if you have a lot of computers under NAT, and also if you think about DNS, it's the same problem, because usually if you're connecting to some web page, it's your connection. But DNS is shared, so if you are doing something normal, you are generating DNS packets. But the malware is also generating DNS packets, so they are getting mixed, and actually it's very difficult to separate. That's why I was saying that we are looking at the group of behaviors and how we can decide if you're infected or not based on that. So if some tunneling is matching a model, but there is no more indications, say, so you are not infected. For example, Tor, right? Or stuff like that. So Tor is very, at some point, for example, Tor, you have an HTTP connection time. Thank you very much. An HTTP connection that is downloading part of the stuff in Tor. So you can detect that and say, OK, no, this is Tor behavior, right? But it's actually very hard to do that. Yeah, it's true.
So I'd like to thank Sebastian very much
Thank you
for
very much.
information on some really cool research.